Hello, today we're going to talk about diodes. Diodes are, we touched on them last time. They're a single PN junction, kind of like a sandwich with a P junction on one side and the N junction on the other. The thing about diodes, the thing to remember is that they're like one-way valves. Okay, if you have water going through a valve, it only passes in one direction. In this case, it's electrical current. Current can only pass in one direction, okay, and we'll see why and how that works. There's a lot of different kinds of diodes. We're going to look at some pictures of them in a minute, but diodes are normally used in power supply circuits to, for example, to change, convert AC current into DC current. They're very good for that. They're also used as protection devices on external circuits, things that go to the outside, for example, on connectors on PCs and your phone and so on, to protect large currents or voltages from entering into the circuit. They'll block those spikes, if you will. So they're all over the place, and there's some special kinds of diodes too that we'll touch on as well. But the most important thing to remember is that a diode is like a one-way valve, okay? Here's a circuit, a little series circuit, okay, and you bias a diode by putting a resistor in series with it, okay, and current's going to flow from the, this is called the anode of the diode, and that's the cathode of the diode. This is the schematic symbol for a diode, a little triangle with a bar here, okay. So the current's going to flow out from the top, the plus terminal of the battery through the resistor into the anode, and then out the cathode and then back in through the battery again, through the power source. Now, there's a bias voltage that's required that's got to be greater than the barrier potential. Remember the barrier potential from last time. Now, the barrier potential for silicon, which is what this diode is, we know that's because it's about 0.7 volts. It varies with temperature, okay? Most of the time at room temperature, it's about 0.7 volts. But I've seen it even at room temperature, 0.6 volts, and some diodes like 1 in 4001 diodes, those are like a volt, a full volt. Other diodes that are made of different materials like germanium and so on, and something called a Schottky diode, that is, those are like 0.3 volts, they're much lower. And they're very specialized diodes used for, again, for power supplies, and they improve efficiency because of that. There's less voltage lost across them. But this curve is the current voltage curve, okay? So as you increase, right here, A, 0 volts, okay, that's this V bias. And then B is a little bit more voltage, but you're still not there yet, okay? And then finally, when you get enough voltage out of this bias voltage to break down the barrier potential, you all of a sudden get some current, okay? How much current? Well, you can use Kirchhoff's voltage law on this, okay, which we'll do in a minute, to subtract the 0.7 volts from the V bias, and that's the voltage across the resistor. That's what's left. And then you can calculate the current using Ohm's law. Now, what if we hook this up? Well, we'll do that in a minute, but what if we hook this up backwards? In other words, this circuit here has is forward biased. Okay, so the positive terminal goes to the anode of the diode. Here, the negative terminal of the power source goes to the anode. So that's reverse bias. So ideally, there's not going to be any current. IA is 0, right? Because it's a one-way valve. So it blocks any current. However, if you keep cranking up the bias, all right, that one-way valve, so to speak, will break down. And that's what this BR stands for, breakdown. All right. And so as soon as you keep going reverse bias, you get this knee. It's a breakdown knee. And this voltage varies depending on This breakdown voltage is, depending on specification of the diode, will vary depending on the particular diode. All right, usually it's much higher than the barrier potential of 0.7 volts for silicon. It's in the tens of volts. Okay. Now there's certain diodes, perhaps some of you have heard of these. They're called Zener diodes, and they're designed to operate in breakdown, reverse biased. And this knee is very sharp, and this vertical line here is very steep. So it actually results in more of a voltage reference. Okay, and we'll get into that later. But the thing to remember here is that when you reverse bias a diode, generally there's no current going through it. Okay, there's three diode approximations. Okay, one is ideal, one is practical, all right, and one is complete. I think I've got all of those. Yeah, there's the practical and there's the complete. All right, so the ideal approximation, okay, is that at 0 volts, you get full forward current, all right? If you reverse bias, you get 0 current. So in other words, the barrier potential is 0 volts. That's ideal. We don't use that very often. What we do use is this one here, the practical. So the forward voltage is 0.7 volts. And then the reverse current is 0 volts. Or I mean 0 amps when it's in reverse bias. That's the one we normally use, okay? And then for the complete, this should have actually another curve coming down here showing the reverse voltage. It doesn't, it should. But this includes a certain amount of forward resistance. That's why this curve is like this. That's why it's slanted a little bit. But we still have the barrier potential here at 0.7 volts. Okay, but we also throw in this resistance curve because the diode is not perfectly a perfect conductor, if you will, and when it's forward biased. There's still a certain amount of resistance, and that's what this indicates. And that's what that says. So here, we're going to do a little exercise here. We're going to use a practical model to determine the current in the circuit, okay? So this is Kirchhoff's voltage law. So the V bias minus 0.7, here's 12 volts, minus the 0.7 is the voltage across the resistor. That's VR, 11.3 volts. So 12 minus 0.7, 11.3 volts. So what's the current? Is 11.3 divided by 3.3K, that's Ohm's law, and we end up getting 3.4 milliamps. And you'll need to do this on a quiz or a test that's coming up, but it's not too bad, I don't think. It's a little different than what your other Kirchhoff voltage law is because this is a fixed voltage, 0.7 volts. It'll always be that. Well, unless you overload the diode or exceed its current capability. You can change this resistor all day long, make it 5K, make it 30K. You're still going to get 0.7 volts here. Okay, so that's the only difference. Okay, here's some different pictures of diodes, all right, all different kinds. Here's a very simple one. This is like a 1 in 914 or 4001 we would use in the lab normally. Some of these are rather large. You see this stud-looking thing. It's got a screw on it and a bolt. And this is for large power applications. Okay. The power in a diode, remember power is voltage times current. What's the voltage in a diode? 0.7 volts, right? Multiply that times the current going through it. That's the power in the diode. So this diode here with a metal thread and stud, and this one here too, which is a little tab, is 220 package, which allows it to be connected to a heat sink, mechanically anchored to a heat sink, so it can dissipate lots of heat and dissipate a lot of power. So there's a lot of current going through these diodes. All right, used for power supply applications. This one's down here as well. The A stands for anode, the K stands for cathode. I don't know why they use K, because it starts with cathode, starts with a C, but that's how it is. The little band on these diodes, very common, that's the cathode, always. When you look at a diode, sometimes you have to hold it up to your eyes real close to see it, but that's the cathode, okay? These surface mount parts, you can't tell as easily. You have to look at the data sheet. Sometimes they're marked, sometimes they're not. Okay, what do we got here? Some key terms. Electron is a basic principle of negative electrical charge. Valence is related to the outer shell of an atom. That's really where all the action happens. That's where all the exchange of holes and electrons happen. And the free electron is an electron that's required enough energy to break away from the valence band of the parent atom and go to the one next door. It's a conduction electron. That's current flow. That's electrical current. And a conductor has a lot of these free electrons. Okay, they're all ready to rock. They're ready to go, ready to travel to the atom next door. And an insulator does not have any of these free electrons. They're tightly bound to the nucleus. So it's not going to give up easily. It still will if you put enough through it, right? Like lightning, it'll blast right through it. There's enough free electrons in it anyway. But generally speaking, an insulator will not pass any current. A semiconductor, somewhere between conductors and insulators. It's got a few electrons that are free that need to be coaxed. How? Electrical current, heat, sometimes light. That's how solar cells work. Okay, solar cells are semiconductors. That's all there is to it. And light allows the current to flow. A crystal, we haven't talked about that. A crystal is a homogeneous structure. All of the atoms are arranged in a symmetrical pattern. Okay, and we talk about crystals, I think, later on in the course. They're used for generating resonant frequencies, or not fixed frequencies. They resonate at a very specific frequency. So they're used for microprocessors and things like that. A hole is basically a missing electron. So it results in a positive charge. Remember, electrons are negatively charged. So if you remove an electron, you end up with a positive ion. And a diode, this is what we just talked about, it's a single p-n junction that conducts current in just one direction, like a one-way valve. The p-n junction is the boundary between two different types of semiconductor material. That's like a diode. That is exactly what a diode is. When we get into transistors next time, we'll see that there's a p-n and another p junction, or n-p and another n junction. It's two junctions next to each other. It's like a sandwich, but we'll talk about that next time. But for now, the diode is just one p-n junction. Barrier potential is the voltage required to produce full conduction across that p-n junction. And forward bias causes a diode to conduct. A reverse bias diode ideally will not conduct until you keep going with it, and then it will break down. Okay, a little quiz, a little review quiz here. Semiconductors, a crystalline material with strong covalent bands, or bonds, between neighboring atoms. Okay, there's strong covalent bonds, I'm sorry. So you have to pass a little current through them and present a voltage to move that current. How much voltage? At least the barrier potential, right? Got to get past that. Metallic conductor has lots of free electrons. Okay, many free electrons held by the attraction of positive ions. In semiconductor, the concept of energy gap is used to show the difference between the energies of conduction band and valence electrons. All right, so you go from the valence band to the conduction band, sort of a visual, if you will. Now these in conduction band, all the electrons are moving between from atom to another atom, all right, out of their valence electron band. An impurity, such as antimony, we looked at a couple different ones. There's 5 electrons that are shown. When silicon has antimony impurities, okay, an N material is formed. Okay, we can use boron instead of antimony, and that would create the P material. All right. Compared to a P material, energy level in N material is lower. There's a slide that talks about that. Those electrons are further away from the nucleus in the conduction band, therefore they've got lower energy. Remember, the further away from the nucleus, the lower the energy. Okay. P-N junction is formed. Electrons move across the junction to fill holes in the P region. Filled hole is what? It's a negative ion. Okay. It used to be positive because it was a hole. Put an electron in there, makes it negative. Forward bias knee voltage on a semiconductor diode is approximately equal to barrier potential. Not the breakdown voltage. Breakdown voltage, that's the other way. All right, that's the reverse bias. Okay. Forward bias knee voltage is the barrier potential. 0.6 volts in silicon, about 0.3 volts in germanium, different type of semiconductor. But as I said, it varies from diode to diode, and there's hundreds, thousands of different kinds of diodes. If you want to know how many different diodes are, go on digikey.com. Some of you have heard of digikey.com, digikey.com, and just type in diode. You'll see how many there are. It's a great website. Number 8, using an ideal diode model, the current in the circuit is shown is now the ideal model says that the barrier potential is 0 volts. Remember? Okay. So if this is 0 volts, that means it's basically a wire across this diode. So 8 volts divided by 10K, 0.8 milliamps. That's what Ohm's law says. Using the practical diode model, which is what we usually use, okay, we now have 0.7 volts across this diode, the forward voltage, okay. So 8 volts minus 0.7 is 7.3 volts across the diode, across the resistor. 7.3 volts divided by 10K is 0.73 milliamps. Okay. And the diode model, which includes the large reverse resistance, is the complete model. Okay. It also includes the forward resistance, so everything is there. All right, and that's what that slanted line is in the graph that we showed earlier. So here's the answers to those, okay? All right, next time I think we start getting into transistors. If I'm not, I don't know, we get into some special kinds of diodes. No, we get into special diodes, okay? So we're gonna be talking about perhaps some power supply. Yeah, we start building things. Power supplies and rectifiers and things with diodes. So we start making circuits right away. How about that? That's cool. And then we'll get into some special diodes the next time. Okay? So everybody take care. If you have any questions, please use the discussion area on the Canvas site. And good luck and stay healthy.